Well, welcome to our Chemtronics webinar, Conformal Coating Defects When Things Go Horribly Wrong. We should have a great turnout today. We have over 250 people registered to attend. And I think there's a natural curiosity when we have an opportunity to see a train wreck. Hopefully you don't want to have one of your own, but if you do, hopefully we can offer you some tips to help you get through the problems, give you some solutions. Okay, so first, some quick housekeeping. Questions are going to be saved to the last 15 to 20 minutes. If you have a question, use the Zoom controls. They should be at the bottom, okay? And so type one in and then submit. And I'm going to get through those on the fly at the end. Now, if there's too many questions to cover live, we'll follow up with answers in an email. Now, if you have something that's sensitive, proprietary, okay, you can send it to me with the word private on the top and with your information, with your name, and we'll get back to you by email or by a phone call, but we won't post it to the group. Okay, so we can deal with that as well. And of course, we'll provide our contact information within this presentation, so you're welcome and encouraged to contact us directly, because we're here to help you. That's what we do, okay? So we really do want you to reach out to us. Now, one final thing, there is a poll, okay? It may have asked you from that at the beginning. If you closed out, that's fine. You can go back to the poll. It's going to ask you questions like, you know, how did we do? Okay, so give us honest feedback. We want to learn from this. And also, we want to know what you want us to cover in the future, because we want to keep coming up with these great presentations to help you guys out. There seems to be a need in the marketplace with the pandemic and everything, with conferences being canceled, IPC, Cleaning and Coating Conference being canceled. There's a need, there's a demand for these out there, so we want to help fill that gap. So now for some introductions. Okay, I'm Kevin Pulowski. I'll be acting as your moderator, and I'll be covering a few slides as well. I've been marketing manager and applications manager for these products for about 18 years. I've done field work and training all over the world. If you call, email, fill in a form, send in a chat, it's generally going to go to me. So I'm easy to get a hold of. So any questions that come up moving forward, please reach out. Now, our main speaker today is the esteemed Pierce Pilon, senior field engineer. And he's also been doing this and previously managing the lab for about 18 years. He started about 6 months before me. So Pierce and I have been through a lot together. Before this, he worked in the petroleum industry for Getty Oil and Chevron. He's very active in SMTA and IPC, having served on various boards and committees, and even speaking at the conferences. He's served as in executive capacities for the Southern Aerosol Technical Association, or SATA. So if you run a conformal coating process, you know how touchy it can be. The goal of this webinar is to give you an understanding of the various problems that come up and what to do about it, how to narrow down the common root causes and find your solution. So we can't cover everything, give you every solution, but hopefully we can narrow that down and give you those root causes. So let's start with a quick overview of conformal coating and catch you guys up. Those that don't do it every day, okay, then we'll catch you up. Now, I do have somebody that raised their hand, and I got to warn you, I'm not going to be answering that, so I'm going to take that as a wave, as an applause that we said something particularly clever, because of course we've got a lot to cover today. So if you can think of conformal coating as a carefully engineered shellac for the circuit board. Okay, like a shellac, its job is to protect what's underneath from the environment. A good coating is going to coat over the contours evenly, including the components, be lightweight, flexible, resist humidity and temperature, and of course, not impede the functioning of the circuit board. So the main point of coating is to increase reliability and maximize service life, of the electronic device, regardless of the environment. Okay? It should prevent leakage and arcing, protect against contamination, and insulate sensitive components. So how do you know if a given coating will do the job for you? There are industry standards that provide testing parameters that can act as general qualifiers. They're from IPC, UL, many of which are adopted and modified from military specifications. So with that overview, let's turn this over to Pierce and let's learn more about conformal coating defects.
Okay, well, thank you, Kevin, for the introductions and the overview. And just a couple of remarks before we get started. First, I'd like to point out that unless it's otherwise credited, that the pictures in this presentation are by permission and are from an SNTA workshop that was held in Minneapolis in 2014. I'd like to thank Doug Pauls of Collins, Jason Keeping with Celestica, and Tanya Martin with SMTA for allowing us to use these images. So now our little disclaimer, this webinar is not meant to be an all-inclusive, in-depth discussion of the conditions that may be deemed as a coating defect, but rather a broad overview intended just to familiarize you with establishing and refining your coating program by recognizing these conditions. So with that, let's get started. Okay. First, you have to define what a defect is. And this can be determined in three broad manners. It can be determined by internal documents that your company generates through your engineering staff, your operations staff. It can also be customer driven, whether it's an internal customer such as, for instance, let's say you have a company with many divisions and your area has been tasked to provide a part for another division of your company. That's an internal customer. Also, it can be customer driven by your outside customers. Contract manufacturers know exactly what this is. Those are determined by contract and the documents that are referenced and spelled out in those contracts. They can also be determined by adoption, either in full or part of industry standards. And two of them that are widely used out there in the manufacturing field are IPC A610 Revision G, that's the acceptability of electronic assemblies, and also the IPC J Standard 001. I believe it's Revision F is what we're on now. And that's the requirements for soldered electrical and electronic assemblies. So now that we've decided how this criteria is determined through your company and your staff, we really need to go through, let's see.
I'll get it for you.
Control, Kevin.
Is this the one you want? One more.
Now, let me see if I can do it. I apologize, ladies and gentlemen. It was working just a little bit ago.
I just advanced it, Pierce. Do you want this one or the next one?
No, let's go back. Okay, yeah, now let's go forward. I'm not sure why I don't have control.
I'll take care of it.
These things happen, people. Okay, a defect versus a process indicator. A little background, a little backstory. When you establish your criteria, there are three main categories of criteria, maybe four. The first is your target properties of your coating. Essentially, this is a wish list of what the perfect coating on your assembly is going to do. Okay, what properties that has to show for acceptance. That is your wish list. The next is actually your acceptance criteria. They may not meet your target, but this is what is considered acceptable. And from there, you can further define the criteria for deeming it a defect. And of course, in there, there's inspection criteria, the methodologies you use, and so forth and so on in your quality process. So with those three main categories, your target properties, your acceptance criteria, and your defect criteria, you've got those established by whatever means you're going to use. We're going to use IPC A610 as our prime set of examples throughout this presentation. And a defect is a condition. And let's be quite plain in what a condition is in this instance. It's a condition that does not allow, and I'm paraphrasing, the form, fit, and function of that assembly in its service environment. A process indicator, on the other hand, is a condition. It is not a defect. It's a condition that points out a characteristic, but it does not affect the form, fit, or function of that product. And it's important to understand that a process indicator neither fully meets the acceptance criteria, yet it's not a defect. And I'll give you a really good example, and we'll see this later on. Let's just say bubbles and voids are considered as conditions that may be a defect, okay? In one area of the board, then that might meet your criteria of a defect. But let's say you have a bubble or a void over on a totally empty, non-populated section of the board. Is it a bubble or a void? Sure it is. But is it affecting the form, fit, and function of that product? If it doesn't, then it's just a process indicator. Is there something wrong? Yes, your process is out of control in some manner, and you should address it and you should resolve it. But based on this criteria, it should not be considered as a defect. That's the difference between a defect and a process indicator. Okay. Next slide. There we go. Okay. Now, as we said, we're using A610 as our source document for this. And these are the criteria that are spelled out in A610. Your criteria may be different, but in A610, this is the criteria that they use. If a coating is not cured, well, that's kind of common sense. If a coating is not cured, it's not functional. It's not providing the protection that you're putting it on there to provide. An example of this is silicone coatings. Many silicone coatings are RTV coatings, polymers, room temperature vulcanization. And as such, they require a minimum amount of moisture to initiate that cure mechanism. So let's say you're in Phoenix in the middle of August, and that relative humidity in the facility is essentially nil. You may get incomplete or just partial curing on your coating. That can be resolved, but at that point, that condition, according to A610, is not or is considered as a defect. That's just one example of coatings not being cured. Okay. The next is coating is not applied to the required areas. Now, those required areas generally are spelled out in your engineering drawings for that assembly. And it's pretty easy to compare that drawing with the actual assembly and look and see during your quality inspection if all areas that require the coating are coated. Now, the flip side of that is you have coatings on areas that are required to be free of coating. These are your keep out areas. For whatever reason, those are deemed by the engineering drawings that they cannot have coating in that area for whatever reason by the designs. An example that was applied and may have been wicked into a connector housing because it wasn't properly masked or booted. And now you have insulated coating around conductive pins or a conductive female housing in the other half of that part. That's just an example. Okay. Let's see if it'll switch the slide. I knew hey, was that you or me? Okay, coating defect criteria, moving on. If there's any bridging of adjacent pads or the lands or any exposed conductive surfaces that are caused by loss of adhesion, voids, bubbles, de-wetting, cracks, fish eyes, flaking, any entrapped material, FOD, that's entrapped in that coating that bridges the lands or the conductive surfaces, adjacent conductive surfaces. If the circuitry is exposed, if it's less than the minimum clearance between the components, lands, or conductive surfaces, that's considered a defect. Also, discoloration or loss of transparency. If a coating has been discolored by the environmental conditions, its surface environment, for instance, urethanes over time, if they're exposed to sun, have a tendency to yellow. If it hazes in any way, it's considered at least a condition to consider deeming it a defect. And the reason this is important is because the inspectors, the end users, if it's set up for rework, they have to be able to see through the coating for labels, markings, anything that they wish to inspect. Okay, the main causes for defects. Now, Kevin has designed this little chart, and we've decided to bring these conditions into three main categories on where they may be looked at as part of the cause. Also, and Kevin was very smart about this, he's created these little symbols. And as we go through this and we hit all of these different conditions that may be considered as defects, you'll see these little symbols up on the top right-hand side of the slide. And that gives you areas to look at to address that condition and find out a root cause to resolve it. Okay, cleaning, or perhaps lack of cleaning. That's one big category where that can be ripe for creating these conditions that may be defects. And you can isolate that. You can take a new board or a new assembly, coat it, and see if it corrects that defect. And then, of course, you want to validate that by additional testing. It could be an application error, an equipment setting, whether it's an improper setting or whether something has drifted. Wet film thickness, if it's too little, too much, that can cause that condition to possibly be a defect. Viscosity changes. Variability, and by variability, I don't necessarily mean in equipment, it's human variability, the human error that's introduced into your process by inconsistency of operator application, whether it's from one application to another using the same operator, or the same application using multiple operators over a shift. You're going to get some inconsistency. And sometimes this inconsistency may result in a condition that could be a defect. And then, of course, you have the curing process, the time, temperature, in some cases, the humidity conditions in which you're curing that coating. If you're not doing it properly, if you're not following the coating manufacturer's recommended guidelines, that could set you up for a coating failure or a defect. Okay, uniformity, or in this case, non-uniformity. The coating, as Kevin mentioned, must uniformly cover that board and all of the components. If it does not, it could be a condition that may be a defect. Now, I'm not sure how many of you know what shadowing is. Shadowing is caused by the geometry of the board, where you have a short component right next to a tall component. And your method of application may prevent that shorter component from being uniformly coated, just because it's being blocked by the taller one. That's what's considered shadowing. If you have any uneven coating application, that could be cause for concern. Brushing is an example of this. When you're using a brush to apply the coating, you're generally going from the beginning of your pass to the ending of your pass on that brush stroke. You're going to apply more coating at the beginning of the pass and less coating at the end of the pass. There's also coating sag, and you'll see this in dipping. Now, I do have to point out that this is specifically addressed in A610. It is allowed. But as the coating settles from a dipping process, it accumulates at the lowest point. Could it be a defect? Possibly. But it is allowed as long as it does not affect the form, fit, or function of that component or that part in its service environment, the end-use environment, then it's not considered a defect, at least according to A610. Your criteria may be different. If you have sharp surfaces, solder points, when coating is applied over these, they tend to be less consistent there than they are on a flat surface of a component or on the board laminate. A solder point essentially is an upside down cone. When it's applied over the top, it tends to fall by gravity down to the base. And so you generally have a little bit less coating coverage at the tip of that solder point. That may be concerned, and it may be cause to consider it as meeting the conditions of your defect criteria. You can have differences in the surface tension of the coating liquid as opposed to the substrate energy, and that can cause non-uniformity. In general, and this is in general, the liquid coating surface tension must be less than the substrate energy to allow it to flow for adequate wetting and adhesion and bonding energy to that substrate. Now we're getting into, and we have labeled these as common defects. Consider these as common conditions. Common conditions. They may or may not be a defect depending on how your criteria are set up. De-wetting is essentially where the coating pulls away from that surface because of differences between the surface energy. It could be a contaminant on there. As mentioned here, it could be little spots of silicone oils from mold releases, adhesive residues. It could be oils from your hands and your fingers from handling the board if you're not properly taking those precautions. Again, surface tension and surface energy variations. That coating is not allowed to properly wet and then bond to that surface. You can have some interaction with flux residues because of the binders, the rheology modifiers, the ingredients, let's say, that's left over after the soldering process in these residues sometimes do not allow proper wetting of the coating. And again, interaction with the coating and the surface. It's because there are just differences between the surface tension of the liquid and the surface energy of the surface, whether it's a component casing, whether it's a board laminate. You see this in the bottom right-hand picture, that obviously that coating is not leveled out and adhering and wetting that entire surface. Fish eyes, my favorite. Compare an actual fish eye with the fish eye on the right. They almost look the same. By and large, this is a point contaminant issue. And when I say a point contaminant, it could be a little spot of silicone, a little spot of oil, wax, possibly some unremoved or flake coating if you've got a rework area going on. What that does is as that coating goes over that little point contaminant, it raises up and it repels from that contaminant and it forms this, it's almost like a bubble, it's actually a bulge, if you will. Another source, I mean, it could be bits of scoring dust, it could be junk coming in from your ventilation system, could be a piece of lint off of your smock. Anything that can settle on that surface prior to coating can be considered as a point contaminant or a potential point contaminant. And I do want to mention here one thing that I didn't put on the slide, but I've seen this quite a few times. If you're using temporary solder mask in your process to protect from, areas that you don't want soldered, let's say if it's a peelable mask, once the soldering process is completed and you peel that mask off, there could be a little spot of residue on there that you don't see with the eye. That can be a point contaminant. If you're using water washable temporary solder masks, those are generally composed of either clay-based or cellulose-based that are in an adhesive binder, a water-soluble adhesive binder. When it goes through the cleaning process, it's washed off, the binder's dissolved, releases either the clay or the cellulose, and then it goes where it goes, down the drain. But if you don't adequately clean it, now you've got little spots of clay, and these are very small particulate size of the clay or the cellulose. Those could be point contaminants. So I'm just pointing this out that there's a variety of sources of this for that. Now, I did include, no, go back, please. I did include this last one, using a thinner instead of a solvent cleaner on the surface. If you're cleaning an area, especially a rework area, don't use the same thinner that you're using for your coating if you have like a selective spray system or a spray gun, because sometimes that is not the proper solvent to clean those residues. And what that ends up doing is now you just smear that residue around that area. It just doesn't properly dissolve and remove a lot of these contaminants. So please be aware, those are other causes of fish eyes. Voids and bubbles, okay? Bubbles are essentially caused by, in the most part, by solvent that has flashed off. Now it is vaporized and is trying to escape that coating, and it can't. So it bulges that coating. What happens is that coating skins over faster than the solvent can flash, and it's trapped. It will slowly diffuse out, but now that coating is cured just enough to maintain that bubble shape, and it can create a void. Is it a defect? Depends on your criteria. According to 610A, maybe. If it satisfies that bridging criteria, then yes. But let's say it's way out on the edge of the board somewhere. It's in a non-populated, just a blank area. It's uninhabited by components. You may have a bubble. Is it a defect? Well, it depends. If it does not fit that criteria, if it's not bridging lands, adjacent components, whatever criteria you have set up, then it's a process indicator. Something has gone wrong in your actual application of that process, and it should be addressed and it should be resolved, but it's not a defect. Now, you'll see this phenomenon a lot at the base of leg components, where you have applied the coating over the top around the adjacent areas, and some of that coating is now in that underfill area, in that standoff area underneath the component. So you're going to apply thermal heat or a thermal cure process. Well, obviously, being exposed to the heat around the edges there, that coating is going to cure at a quicker rate than the coating in that standoff area below the connector, or not the connector, but the component, excuse me. So now you're starting to cure and skin over that coating at the base and around the edges of that component. And now the solvents underneath are starting to flash. They're picking up that heat. Well, they've got to go somewhere, and they want to go out from underneath that component. And they hit that partially cured or initially cured coating, and because of the vapor pressure, it causes that coating to bulge and create a bubble, okay? Those are especially common. Now, if you're brushing, when you dip your brush in the coating, it can trap bubbles between those bristles. And then when you make your pass with your brush, it releases that coating with the entrained air bubbles in there. And sometimes those bubbles will dissipate as the coating levels out, and sometimes they become trapped. So that's a condition to warrant further inspection. If you're using a spray gun, improper setup, or your settings have drifted, they can trap air bubbles. If your travel pass across that board or across that assembly is too slow, it can entrain air as it hits the surface of the board, okay? Possibly air that's underneath that component that we just talked about. If the distance between your nozzle and your substrate is too close, now you've introduced some turbulence in that coating as that higher pressure coating hits that surface, and that can trap bubbles. If your air pressure, and by the air pressure, I'm talking about your push pressure, either in your selective system, which you generally don't see that in a selective system, but it can happen. It's more obvious in a spray gun. If that's too low, it can entrain bubbles. Cracks and ripples. These are actually some very good pictures. If you have excessive coating thickness, if your wet film is way too thick, and especially if it's a high solids content coating, it doesn't cure evenly. It doesn't allow that solvent to evaporate evenly, and especially at the surfaces. And then you get strains and stresses in that coating, and it cracks. If you're force drying, if you're curing at too high of a heat, it can create cracks. The bottom left-hand picture there is what we call mud cracks. It's also evident in the bottom right-hand picture around the component labeled as 105. You can see the crack across just outside the top of the component on the top edge in the picture. That's just caused by uneven curing and stresses and strains within that coating as it tries to cure, and it just cracks. Delamination. Delamination is not common, but it does occur. And the bad part is you're generally not going to see this in your manufacturing facility by your inspection team. One of the causes is, again, excessive coating thickness. That interface of the coating at the substrate is improperly cured, or it does not cure at the same rate as the rest of the volume of that coating, and it does not allow for good adhesion with the substrate surface, whether it's a component or the laminate on the board, whatever it may be. Various surface contaminants can prevent good bonding. If you have a little silicone on there, maybe you've got a part that's a peel off that's stuck on there, any of those can prevent good bonding. If the substrate energy is too low, number one, it's going to feel very slick. Just on a bare board, it's going to be extremely slick. If it's lower than the surface tension of that coating, it can cause delamination. Now, what it's going to look like is it's going to look good. It's going to look like it's bonded to that surface. But 6 months down the line, it's going to pop up. That adhesion is going to fail. Sometimes they just flake. You can see up at the top, in that top picture, you can see areas where that coating is just kind of flaked off. In the bottom, they're flaking, but it looks like almost the entire coating has pulled up from the substrate. Now, if you're doing multiple coats, and I'll throw this out there, we always recommend to do, if you're doing multiple coating, use thin coats, not heavy wet coats. Multiple thin coats is a much better adhesion practice than heavier coats. They just don't tend to meld together. okay? And we always recommend on the previous coat, allow it to become tacky. Don't overcoat it while it's still essentially wet. You're running the risk of those coatings not adhering to each other. Actually, that's called cohesion. Orange peel. It looks exactly like it sounds. Okay? It's a very rough, very uneven texture. You can see that. Actually, you can see the texture in the picture of the orange peel, but you can see it in that bottom picture on that component. Sometimes excessive film thickness and using heavy wet overcoats will cause this. Sometimes if you have a wet coat and you're applying another coating on top of it, that pressure from an aerosol, from a spray gun can kind of push it. And as that bottom picture, you can see the coating on the left-hand side looks thinner and it looks like it's been waved up over to the far right-hand side. And you can see kind of the peaks and the valleys and that uneven texture there. If your substrate is too warm relative to the temperature of the coating, it can cause this. Let's say you just cleaned your board, it's gone through the dry cycle in your wash system, you take it out and it's still warm, but you're in a hurry and your operators need to coat it. Well, now they're applying this coating. And what happens is that as soon as it hits that warm substrate, there's such a delta there that solvent starts flashing, and it's flashing unevenly. And this is going on as you're depositing additional coating on top of that. And so with solvents starting to flash in kind of a random manner, and they form these bulges, and they form that really uneven, rough, peak and valley type texture. Now the next one is not necessarily an application issue. It may be the product. It may be the wrong coating, okay? If the solvent evaporation rate is improperly staged, it won't level. And by that, what I mean is when a coating manufacturer is developing the coatings, they pick solvents and they pick the amounts of solvents where it allows for a staged evaporation rate. And most formulators will include what they call a tailing solvent. It is generally the smallest amount of solvent, yet it is the slowest evaporating solvent. And that allows that coating to remain wet in the final stages of curing to allow it to level out to that nice, smooth, even finish that you've come to expect. But if it's not staged properly, if it just flashes out too quickly, you're going to end up with a lumpy mess and or orange peel. If you're spraying, especially spray guns, again, pressure too low, it can cause this. Again, if you're spraying, on this last point here, your passes across that board must be parallel to each other and at the same distance with a slight overlap. And they have to be perfectly perpendicular to the substrate. If you're spraying at an extreme angle, you're putting pressure behind that coating. And again, it can push that coating at the point of contact. You can push it away from that point of contact on your previous coat. So, and it can result in orange peel. It can also result in other conditions for potential defects. Wrinkles and waves. Well, I tried to get Kevin to put a picture of my great-great-grandmother up here, but he didn't think that was professional. So we just went with a picture of a prune. And that's exactly what wrinkles look like. They're just real rippled, real wrinkly. And there's a couple of causes of this. One of them is that if you're curing in an oven, if you're curing in an IR conveyor system, that thermal cure energy is too high. And that tailing solvent flashes too quickly. In other words, all of your lighter end solvents are flashing, but your tailing solvent is flashing at the same time. It's just too much heat for it to handle. It needs to be done in a staged manner, and you're going to end up with a wrinkly, lumpy mess. If your previous coat is still wet and you're coating over that, instead of letting it come to a tacky condition first, it can create that wave effect like we kind of discussed before. It's just kind of pushing that coating away from that point of contact, and it looks like waves lapping over one another. And again, this is a condition that can be a defect. The question to be asked, according to 610, is does it ensure the form, fit, and function of that part in its service environment? Okay, here's a different take on that same chart that we had earlier. And now what we've done, we've kept the main three categories of generic causes here. But what we've done is we have included these conditions that we've gone over, and we've categorized them according to a cleaning issue, an application issue, or a curing issue. Now, they're not mutually exclusive. If you can see, delamination can be caused by a cleaning problem. It can also be caused by a curing problem. That's why we put those little symbols up there. Sometimes there's one little symbol, sometimes there's multiple symbols. But hopefully, this has given you at least some areas to investigate so you can resolve that problem. All this is for your benefit.
All right, Pierce, is that you done? You ready to?
No, we've actually got another one, and I can't get it to go.
Oh, I'm sorry.
There we go. There we go. Okay. Cleaning your PCB before coating. Well, here's the deal. Coating loves clean. The cleaner it is, the better chance you're going to have of good bonding energy, good adhesion, good coverage, and less potential defects. And non-cleaning or improper cleaning or lack of cleaning, these are common causes of like fish eyes, dewetting, delamination, flux residues if they're not clean. They can absorb moisture, cause corrosion even under the coating. So we recommend that your assemblies be clean before your coating process. And this is including no clean fluxes. And a little word about no clean fluxes. No clean doesn't mean you shouldn't clean. And the reason that no clean fluxes are called no clean is because the residues do not, according to the manufacturers, contain any ionic ingredients or any ionic portions of that residue that can promote dendritic growth. However, no cleans, as well as a lot of other fluxes, can cause reactions with the coating, cause adhesion issues. There have been some instances where these are routed back to the use of no clean fluxes. It is not every no clean flux. It is not every coating. It's just certain combinations. People coat over no clean every day. But that potential exists for that 1 in a million shot of having a coating and a no clean flux residue that are incompatible with each other. So we always recommend cleaning before you coat. And you can avoid these coating failures due to surface contamination, such as flux residues, release agents, silicone contamination, adhesive residues, scoring dust, junk from your ventilation system, whatever it may be. Anything that settles on there or is on there due to the assembly process, the soldering process, anything like that. Those are all potentials to cause problems in your coating process. So please avoid those clean, and you'll have a whole lot less agony in your life.
Okay, so thank you, Pierce. I think we've got like expected, like planned. We've got 15 minutes for some questions. We do have 3 questions. Actually, 4 questions. The first one is a marriage proposal. We won't get into that one. Okay, so we've got one. We are using your coating, Texbury 2125, and we'd like to do accelerated curing using IR, running PCBA panels down a conveyor with IR heating. Can you help us figure this out? Duration, intensity, temperature, etc. And we do have his information, so we can always get back to him. You want me to repeat that? 2125, curing with IR
2125, okay.
Yeah, and let everyone know that is fine L coat LED 2. So that is a coating that's intended to go over LEDs.
Right. We do have some customers that are utilizing the IR conveyor system, and essentially that kind of has to be done on a case-by-case basis because it depends on the heat mass of the assembly, the speed of the conveyor, the wattage of the IR. I think that honestly is just something as a engineering question for your process people. We can give you some basic guidelines, but that's about as far as a coating manufacturer that we can recommend, because every system is going to be slightly different.
Okay, very good. And we have Ted's information, so you know, we can always get back to you too as you get specifically into that if you need some additional help. Got a couple I can answer. Do you manufacture any UV curable coatings? We do not at this time. Will the slide deck be made available? Absolutely. We will be sending a PDF of this slide deck to everybody in attendance here and to those that may have missed it. And so you can take a look at your leisure and pass it on to your colleagues. Will this presentation be available to watch at a later time? Yes. Okay, so I'll go ahead and skip ahead. There's a number of questions on that. Maybe I should have covered that ahead of time. After this, and it could be end of the day today into tomorrow, I'll be sending out a link of this recording. So you can watch it at your leisure, fast forward to your favorite moments and share it with your colleagues. You'll get a PDF of the presentation and a PDF of our cleaning and coating guide. Okay, so we'll get that taken care of. Got a question pertaining to the subject of substrate surface energy. Does it matter what type of solder mask is used on the PCB? And I guess to extrapolate further, is there a solder mask that may be more problematic for conformal coating?
To be honest with you, since we don't get into the bare board manufacturing part of it, I think that's something that the design engineers need to address. But just as a generality, matte finishes generally work a little bit better for adhesion on coatings in general. Does that mean that they won't go over the nice, smooth, glossy finishes? Yeah, they will for in the most instances. It's only extreme instances when I've seen an interaction between a coating and a laminate. Doesn't mean that there's never any of those, but I have seen them. But that's something that actually needs to be addressed as the assembly is designed in conjunction with the actual process engineer that's going to be picking the materials for the project.
Yeah, and let me give a part B to that one, because I thought of the question a little bit differently. When you said solder mask, you interpreted it as the resist, which you could be
right.
Absolutely what he intended. But let's say temporary solder mask, which is often used for masking through holes, or well, in this case, it would be used to mask off areas that you do not want coating around connectors and such. Are there any temporary solder masks you need to be aware of that are better than others? I mean, besides our brand, of course.
Well, obviously, if you're, okay, yeah, obviously, if you're going to if you're going to use the solder mask to prevent overcoating in areas of keep outs, just for convenience and less muss and fuss, I would go with a peelable, because you're always going to overlap some of that coating or some of the mask with the coating, just for convenience sake.
Yeah, and that actually is a great point. Is real common question of, you know, what type of mask peelable and or washable. Washable is real problematic. Obviously, you put a coating over a washable using it for masking, it won't wash off.
Right.
For peelable, I generally recommend a latex, a natural latex, because those do tend to snap off a little more cleanly from conformal coating. And another trick that I probably learned from Pierce is don't wait until it's fully cured, but when it's just dry to the touch, before you remove that, and that's going to give you a cleaner release, you know, cleaner line from that mask.
And another option, and especially if it's a complex area on the board, you may consider capping or using a boot for that area to prevent intrusion by the coating.
Okay, excellent. Do these conformal coating defects occur when using a nano coating? And I assume they mean like
those are the ultra thin coatings.
Ultra thins.
Honestly, since we don't manufacture the UTCs, that's actually a new category that they brought out in 830 revision C now that they've defined. And I just can't answer that question. I would prefer that you go to a manufacturer that does the UTCs and find out what types of problematic application issues they have with those. I'm just not that familiar to even warrant a good answer for you, and I'm sorry.
Yeah, and Phil, to clarify, Chemtronics, we do not offer nano coatings or ultra thin coatings. Example, 3M has a line of those, so that, you know, we don't have that level of experience. Got a question. We're interested in testing how good the coating is in controlling impedance between components. Any suggestions on how to measure?
Honestly, I would refer you to some of the qualifying procedures in the IPC and the 830 series of tests. If a good source for this actually would be with IPC, you can get with their liaison, Deb Obitz, and she can steer you to either the right options to use or the right people to ask that question. Obviously, you can send that out to like third-party laboratories, but I would actually recommend getting with Deborah Obitz at IPC, and if you'd like her contact information, just please send in another question and we can provide that.
Well, I have his name. So yeah, Bill will send you that information. So not a problem. I've got a question that simply says dendrites, three question marks. And I assume that is a question on whether or not conformal coating can help with dendrites, or what it does to either prevent dendrites or prevent deposition, redeposition, or deposition of the dendrites as they break off.
Well, if you have dendritic growth underneath a coating, that means that you had some ionic residue there.
My apologies. I was thinking of tin whiskers. So dendrites. Okay, so my apologies. Let me clarify. I was talking tin whiskers, totally different subject. Dendrites grow from ionic residues and form dendrites, use branch structures from flux residues. I'm sorry. Please continue, Pierce.
Oh, well, if you're getting dendritic growth, that means that you've got some type of ionic residue underneath the coating. Hopefully the coating mitigates intrusion of liquid moisture, liquid water. It resists that. However, one thing you have to be reminded of is that all coatings are permeable. All coatings will breathe to a certain degree, some more so than others, even within a category. Like within acrylics, there's different transmission rates. It allows that moisture vapor from the outside environment in the humidity to come in. It also allows it to go out. Some are better at that than others. But if you have ionic residue, as soon as that moisture vapor comes into that coating and it condenses, now you have a perfect setup for corrosion and dendritic growth. To address it and resolve it, the best way is just go back to that root and adequately clean that residual off, whatever it may be, whether it's from flux or some other type of residue, and completely clean that prior to your coating process.
Yeah, and you bring up a real good point in terms of permeability of coating. There's a misconception that commonly comes up is dirty or clean, you seal it up with conformal coating to fix it, and that's not how it works. And so it's a really, really important concept to realize that yes, you can make a board water resistant, but you're not waterproofing it with these coatings. They're semi-permeable. Some of this can get in and still continue to react with what's under that coating. So really, really important. So Liam, thanks for your question. Currents undercoating. Okay, he clarified. So I think we've got that answered. In a seal enclosure, what moisture level is required to limit dendritic growth? That's an interesting, that actually, we'll get back to that. That's going beyond the scope of this. And so, but it's a really, really interesting question. So we'll answer that offline. That gets into more of a cleaning issue. I have a question. We've got just a few minutes. So I have a question. You brought up surface tension a couple of times, Pierce. And so the question is, if you're having a surface tension issue, is there a way to test the surface tension of your board and compare it to what it should be, or what the surface tension of the material is?
You can actually a laboratory can test the surface tension of, say, the coating liquid as such. There's dynamic and then there's static surface tension testing. What you have to realize is that as the coating liquid, as those solvents evaporate and that coating becomes more solid, that surface tension is constantly changing from the time you apply it until the time that it is totally cured. When I say the surface tension, what I'm talking about is like the initial coverage of the substrate with the coating. Because once that's on there and it's flowed, it's wetted, it's starting to bond, then that property of surface tension, when you first apply it, has done its job. If it's de-wetting away from the substrate, whether it's a component casing, whether it's a thermistor, whether it's the laminate on the assembly itself, there's something on there. It could be the surface of the laminate, but it could be a residue of some sort, maybe even from the board manufacturer. Many companies clean their boards before they even start the assembly process.
Okay.
They'll clean their boards.
Thanks, Pierce. I started that one, so sorry to cut you off there, but we're at the tail end of this, so I appreciate you guys all joining us here. Hopefully this was really helpful. Any other questions, please reach out. I've got our information right here. I'll also, in the email to everybody who's attendance and not in attendance but have registered, you'll get our information as well. Please reach out to us with questions, problems. Let's say you're qualifying a new product, a new process, you're running into problems, okay? Our job is to make your job easier, okay? So please reach out to us. Don't hesitate. Again, you can contact me by that, but also by chat and all this other good stuff on the internet. So as I mentioned, you'll be getting all this material, PDFs of the cleaning and coating guide, and a link to this to pass on. So thanks everybody for joining us. I hope this was valuable to you, and we'll see you at the next webinar.
Thank you, everyone.